So last time we talked about the spontaneous symmetry breaking, which is a new concept in statistical mechanics concerning the phase transition. So this is one of the most important concepts in statistical mechanics. And so let me just make it clear what it means by saying that the system shows a spontaneous symmetry breaking. So remember, last time we talked about the thermodynamic limit, and we mentioned that the phase transition occurs only in the thermodynamic limit. And if we calculate the thermodynamic properties at finite size, and we would not get any non-trivial phase transition or any non-zero order parameter. So in the case of Ising model, we could calculate the free energy density by taking the thermodynamic limit first and then taking the zero field limit later. But we can also do the reverse order. We could just keep everything finite, but we take the zero field limit first. But obviously, these two operations with the different orders of this limit that we take will lead to different results. So the first order is the proper order that we emphasize many times, that we should take the thermodynamic limit first before we do anything. But on the other hand, if we just do the reverse order, and we can still do that, however, we'll get incorrect conclusions about anything that we calculate. In other words, taking the thermodynamic limit by taking the volume, the number of particles to infinity, and taking the external parameters such as field to limits, these two limits do not commute, I mean interchangeable. So if these two operations commute, which means that it doesn't matter which operation comes first and which operation comes later. It's the same results. But apparently, in the case of the Ising model, concerning the phase transition, these two operations will lead to completely different results. So one is correct, another is wrong. The first is correct, the second is wrong. But these two operations tell us something even deeper in statistical mechanics, which means that it introduces the concept of spontaneous symmetry breaking, or SSB. It means that the Hamiltonian of your model system shows certain symmetry. For example, in the Ising model, in any dimensions, and there is a symmetry of the Hamiltonian by flipping the spin on every side. Si, suppose I flip the spin Si on every side to minus Si, the Hamiltonian is still the same Hamiltonian. Of course, we need to be in the zero field limit. So, but this is the symmetry of the Hamiltonian. However, the ground state of that model, which shows that symmetry, doesn't have that symmetry. So we say that the symmetry of the Hamiltonian is spontaneously broken. Just use that definition of this SSB to clarify the statement. So we know that if we use this wrong procedure by taking the zero field limit first and then taking the thermodynamic limit later, then we get no magnetization, even the zero temperature for Ising model, but we know that this is wrong. However, if we take the thermodynamic limit first and then take the field to zero field limits, and this will lead to this finite value, which is the size of the magnetization for the Ising model. And the first line seems to suggest that there is some symmetry. So if we are keeping the system always at finite size, then there's a symmetry between the spin pointing up or pointing down. So there's no preference for spins to point either up or down at any given finite size. So it looks like the Hamiltonian at any given finite size is invariant under spin flip. However, the ground state in the thermodynamic limit breaks that symmetry because once the magnetization and acquire a finite value, which means that the spin moment should point to a particular direction. There is a preferred direction that the spins will point to. So the spins cannot point to any directions, up or down, so they need to choose one of the directions that they want to point to. So in other words, the ground state of the Ising model in the thermodynamic limit breaks that kind of spin flip symmetry spontaneously. the word spontaneous implies that there's no external field. So we don't apply the external field. Of course, when we apply the external field, we force the system to be parallel or to be polarized with the field. But this is the zero field limit. So in the absence of the external field, the spins of the Ising model still want to be parallel to a point to a certain direction, say spin up configuration. And that kind of a symmetry breaking happens spontaneously, meaning no external force. Nobody forces the spins to point up or down, but it just chooses one particular direction to point to in the thermodynamic limit and in the zero field limit. So the symmetry of the Hamiltonian is spontaneously broken, right? So that's the meaning of a spontaneous symmetry breaking. Whenever we have such a spontaneous symmetry breaking, the grounds of the system shows some kind of an order, because in the case of the spin, order states the spins should point to the preferred direction, and that breaks this kind of invariance of the spins that could point to any directions. The spins cannot point to any directions. Okay, so in the case of the Ising model, say in 2D, the magnetization is actually maximized, which is -1, the magnitude being 1 at 0 temperature, and then it decreases at finite temperature until temperature reaches this critical temperature where magnetization vanishes. So when you have such a finite magnetization below the critical temperature, and we call the system shows spontaneous symmetry breaking. So we will come back to this later. To clarify this point, as I mentioned last time, at any given finite size, the free energy density, the bulk free energy density, is actually a smooth function, as function of the field, so that there is no cusp. So when you take the derivative of this free energy with respect to the field, on either side of this zero field limit, you get the same. And then you get zero magnetization. However, in the thermodynamic limit, where this number of particles goes infinity, the free energy density shows a cusp right at zero field limit. In that case, these two derivatives on both sides of the transition become different. Okay, so then you get finite magnetization, depending on whether you come from the positive side of the field or the negative side of the field. But you could just consider this kind of dynamical processes in the following way. Suppose we keep the system the finite size and there's no field, zero field. So you can see that spins could actually point to either up or down, but on average, you have an equal probability to see the spins pointing to the up spin state and equal probability to find the spins pointing down, like this. So if you plot this magnetization that you can measure as function of time, then at finite size, you may see this kind of a periodic oscillations of the magnetization between plus and -1, and those distributions is actually evenly distributed between this plus and minus of this magnetization. Okay? And therefore, if you take a time average of this magnetization that you see, and you get 0, because this plus and minus region of the magnetization function of time just got canceled, which means that the spins could point either up or down with the equal probability. So that's precisely what we mean by no magnetization in any given finite size, because the spins fluctuate between plus and -1 periodically, so on average they got canceled. If we keep this field at 0, but we go to the thermodynamic limit where the system size becomes infinity, then you have a different ground state. Okay, depending on your tiny little bit external fields direction, whether this is a 0 plus or 0 minus. In the case of 0 plus, the spins may be induced in such a way that they all point to up spin direction. So over time, this +1 state is a stable state, which means that you always find the spins point to the spin up direction. So if you take a time average of that system, the thermodynamic limit, you get +1 all the way to infinity of time. So the time that the spin is spending in the spin up state is actually increasing exponentially. So you have no chance that you find the spins pointing down in this spontaneous symmetry breaking situation. So you can see very different behaviors between the system at finite size and infinite size. And that is really the key point that ordered phase could be actually clearly obtained or derived only in the thermodynamic limit. So with that concept at hand, we could just use a slightly different language to further support such argument. And in the following, we're going to calculate the probability distributions between spin up state and spin down state in the thermodynamic limit. Let's just try to calculate the probability distribution for spin up and spin down state concerning this SSB. So again, suppose we keep it at zero field and the temperature is below transition temperature, and state A is a state where this magnetization is finite with the amount of ms, and state B is actually minus ms. Okay, this is the same as the say spin up and spin down state. Suppose we have these two possible states, and we in a zero field limit, we see that these two states have equal probability to be found, and they are linked by the time reversal symmetry. When we simultaneously flip the spin direction and the field direction, and Hamiltonian is invariant for the Ising model in the presence of field. So originally, we consider such a time reversal kind of a pairs of that possible two states and try to calculate this probability for either of these two states, and we compare the probability that we can find, say state A or state B, and see whether they are still equal probability. But to do so, we need to apply a small magnetic field. Okay, suppose that H is actually 0 plus, it's not equal to 0. We just try to apply just the infinitesimal amount of the positive field and see what happened. So we could calculate the probability that we find the spin in the state A relative to the spin in state B. But this ratio between these two probabilities of spin configurations is actually proportional to the ratio between this Boltzmann weight, this e to the minus beta h. But in this case, the ratio is given by e to the 2 beta times the field and this ms times the number of spins, capital M. So this is the relative probabilities that we can find the spins in state A relative to the spins in state B, and it is actually given by this exponential factor, but all these variables here are positive. So you can see that still we keep this system at finite size, but we take the thermodynamic limit. So when n goes to infinity, and we immediately see that this exponential factor simply blows up. So this is infinity. So which means that relative to this state A, there's almost no probability that we can find the state B, because the ratio between PA and PB is actually infinity, which means that the PA is almost 1, but PB is almost 0. Okay? So in other words, for tiny little bit external field along the positive direction, 0 plus, and when we take the thermodynamic limits, the equal probability is actually broken. So now we have completely different probabilities to see the system is in state A compared to spins in state B. And for a positive field, and it is state A, which we always see, and there's no chance that we can see the state B. So that's precisely what happens here. Suppose I apply this 0 plus field, and based on this kind of calculation, and we know that we always find the system in that +1 state of a spin. Okay? And therefore, the previous symmetric equal probability situation between state A and state B is spontaneously broken. Okay? The system spontaneously chooses one of the two states to be the ground state. So you could easily see this difference between these two operations that I just mentioned. Suppose we are taking the correct order of these two operations, and we could just calculate PA relative to PB, but we first take the thermodynamic limit, and then we take the field to 0 plus limit, and this is plus infinity, which favors the plus ms. But on the other hand, so if we just come from the negative side of the field approaching 0, and we do the same calculation, and this is going to be 0. So this is very sensitive to this kind of an initial condition, and we will come back to that later. So depending on your initial condition, you could either make a system point to the up spin direction or the down spin direction. But in either case, symmetry of this up-down spin state is spontaneously broken. So I think that will illustrate the important concept of this SSB. And so let's take a short break. When we come back, we will move on to discuss the continuous symmetry versus the discrete symmetry and Heisenberg model. Okay, so let's take a short break. We know the spontaneous symmetry breaking, but there are two kinds of symmetries that often appear in statistical mechanics. One is the Ising symmetry that we just mentioned, the up-down spin symmetry, so which we call the symmetry discrete symmetry because there are only two discrete values of spins, either plus or minus 1, that can be taken. So we call this Z2. Z refers to the integer, and 2 refers to the number of possible values of the spin. So Z2 refers to the integer, two possible integers plus or minus 1 that the spins can take. Discrete symmetry, and because of this discrete symmetry, the width of these domain walls that we mentioned at finite temperature due to thermal fluctuations must be finite. And in the single domain wall situation, the distance, the width of this domain wall is nothing but one lattice spacing, which we'll come back to that point later, talking about the kind of a discrete symmetry and the consequence of that discrete symmetry. So this is just one possible symmetry often occurred in the many-body system. So there is another symmetry called continuous symmetry, meaning the Hamiltonian is invariant under spin rotations in the three-dimensional space. So the spins can take any values or any directions along the radius direction of a sphere. Okay, so the spins can actually rotate in this spherical coordinates any directions they want, and still the Hamiltonian is invariant. So in such a case, we call this Hamiltonian shifting continuous symmetry. This is the generalization of the discrete symmetry that we are talking about, which is the Heisenberg ferromagnet. So remember the Ising model, the spins can actually point to either plus or minus z axis, but now we generalize this spin orientation on the lattice and to any arbitrary directions in three-dimensional spin space. And therefore, the Si.Sj term in a Heisenberg ferromagnet can point to any directions. So this Si and Sj is actually a vector in three-dimensional spin space. But in the Ising model, we only take this Sz component of the spin vector, but now we generalize it to any arbitrary direction that spin can point to. As a result, in this Heisenberg model, we have three terms: Six, Sjx plus Siy, Sjy plus Siz, Sjz. So the Zeeman term is also generalized to the dot product between this magnetic field vector dotted the spin vector. So this is the three-dimensional generalization in spin space from this Ising model. So there is similarities and difference between these two types of symmetry that we often find in the Hamiltonian of statistical mechanics. But now let's just formally define such a so-called spin rotational invariance of the Hamiltonian in a Heisenberg model. Suppose I define a rotation matrix which rotates my xyz axis by an angle theta about any axis, say x, y, or z axis. Suppose I just perform such rotations on the spin. And if I just plug in this new spin vector after rotation into the Hamiltonian if that Hamiltonian is the same as the Hamiltonian before we rotate the axis or rotate the spin, then we call this Hamiltonian shows rotational symmetry, or this O3 symmetry, and 3 refers to the 3 dimensions. And this is certainly a continuous symmetry because theta can be any real value between, say, 0 and 2 pi. And so we call this continuous symmetry. So the different effects of this continuous symmetry, thermal fluctuations, can be analyzed in the following. So we could say that it is relatively easier for thermal fluctuations to destroy the long-range order when there's a continuous symmetry as opposed to a discrete symmetry. So the reason is there are more directions to point in the spin space. So let me just use the figure to illustrate this point. Suppose I have an Ising model, and we know that the low energy excitation of the ferromagnetic ground state is the creation or the spontaneous formation of the domain wall. Remember that. However, in the continuous symmetry, that the spins can actually point to any directions. So you can imagine that thermal excitations can actually go to arbitrary direction in the 3-dimensional spin space. So they are not restricted to just up or down, but the spin can actually respond to the thermal energy, change their direction to the arbitrary direction in 3-dimensional space, and therefore it is easier for that continuous spins to actually change slightly the direction in response to the thermal fluctuations. So thermal fluctuation can more easily destroy this kind of a long-range magnetic order because there are more directions for the spins to fluctuate. Compared to the Ising model, there are only 2 possible directions that spin can actually flip. But for this O3 symmetry system of a Heisenberg model, there are many, many different directions that the spins can actually fluctuate. So it is relatively easier for the thermal fluctuations to destroy the long-range order when there is a continuous symmetry as opposed to the discrete symmetry. So we will come back to this when we talk about this kind of predictions about the TC between this Heisenberg model and the Ising model. So the TC for the Heisenberg model is certainly lower than that for Ising model because, again, the thermal fluctuations can easily destroy the long-range order compared to the discrete Ising system. So I think that should be enough for this lecture hour. And next time, we will discuss, again, another very useful and important concept idea. It's called ergodicity breaking. Okay, so see you next time.